Okay, so let's continue with the 569, problem 569. If the cable can be subjected to a maximum tension of 1500 newtons, determine the maximum force F which may be applied to the plate. Compute the X, Y, Z components of the reaction at the hinge A for this loading. So we are given a plate, a triangular plate. It is hanged to the ceiling from point B to the point C on the ceiling with a cable. And we know that the cable can carry only tension and can carry load only along its direction. Then it is fixed to somewhere, perhaps a wall, with a hinge at point A. There exists a load acting on the plate. The location of the force is given. It is 0.9 meters away from the y-axis and 0.6 meters away from the x-axis. Certainly, the plate plane lies in the plane of xy, and z-axis is given as perpendicular axis, perpendicular to the plate surface. The dimensions of the plate is given also. So it is 2.7 meters long in x direction, and it is 1.8 meters long in y direction. The location of the hinge is just on the y-axis, and it is 0.9 meters away from the x-axis. The position of the force is 0.6 meters from x-axis and 0.9 meters from y-axis. Now, first thing that we have to do is to draw the free body diagram of the plate. Therefore, we have to look at the joints for this purpose. So first, let's look at the joint B and isolate the joint B from everything. Now, if I look at the joint B, I can see that this joint will restrict the motion in this direction. So the plate cannot go in this direction. As a result, there will be a reaction force which avoids the motion in this direction. So in Z direction, I can easily say that located at point B. Okay. Now let's look at the hinge and isolate the hinge first. Okay, so this is the hinge and let's isolate it. So let's look how it restricts the motion of the plate. First of all, this plate cannot move in y direction at point A because the hinge restricts it. Of course, it cannot move in x direction. So in both positive and negative x direction. As a result, there will be a reaction force in x and y direction. In fact, identically, hinge does not allow the motion of the plate in z direction. In fact, I can easily say that there is a force, reaction force, located at point A with an arbitrary direction, and we don't know what it is yet. Okay, this is something, but let's look at the moment then. Now, certainly, this hinge does not allow the rotation of the plate around x-axis. So because it cannot rotate around x-axis. This means that I have a reaction moment in x direction. Now let's look at the z direction. Certainly this hinge does not allow the rotation of the plate around z-axis. So I can easily say that there is a reaction moment in z direction as well. But as you see, this plate can easily rotate around y. So there is nothing that which restricts the rotation of the plate at point A. Therefore, I don't have a reaction moment in y direction. Now I can draw the free body diagram of the plate. Now this is my free body diagram. I have the tension T. I have the force located at point C. I have Fa, reaction forces at the hinge, and Ma, reaction moments at the hinge A. And I don't have any other forces. I just draw the plate in a schematic way. So O is my origin. In fact, I can easily say that tension force coming from the cable is Tk. It is in the positive z direction. If I look at the reaction force at A, it will have three components. I denoted with Fa, Fax, Fayj, and Fazk. Now, for the moment at point A or at the hinge A, I have Ma. So I have X component Max and Maz. Certainly, the Y component of the reaction moment at the hinge is 0 because it can rotate around Z at point A. Now, since F is given, the direction of the F is given, it is in the negative Z direction, so it is minus Fk vector. Now let us write the position vectors. So beginning from the A, Ra has a position vector of 0.9 j vector, so it lies on the y-axis. Rb is 2.7 I vector, it lies on the x-axis. And the force is located at C, so Rc is 0.9 I vector and 0.9 j vector. Let's check it. Yes, it is 0.6 j vector and 0.9 I vector. Now, I have two equilibrium conditions, and the first one is sum of the forces in all directions has to be equal to 0. So it's a vector sum. This means that Faxi, Fayj plus tension in the cable, because I have only Z component of the tension in the cable, T plus Faz minus Fk vector is equal to 0. This means that coefficients of the unit vectors has to be equal to 0. As a result, Fax is 0 and Fay has to be equal to 0 from here. Then I'm left with the Z component of the forces. So the expression inside the parentheses has to be equal to 0 as well. So T plus Faz minus F has to be equal to 0. Now, next equilibrium condition is sum of the moments has to be equal to 0 as well. Now, this basically means that RB vector product T plus RA vector product FA, RC vector product F has to be equal to 0. Some of these moments, these are the moments generated by the, I'm sorry, that has to be MA as well. Eh? So let's correct it. There has to be MA because I have the additional moment coming from the just a moment. This is A as well. So this is and it has to be equal to a vector sign. Then there has to be equal to plus sign. Okay, so MA. And so it is MA, the reaction moment at A, plus 2.7 I vector multiplication with the force 1500 K vector, because the tension in the cable can be at maximum 1500 newtons. So therefore I can substitute 1500 there without having any restrictions. This is the condition, because I want to determine the maximum force F, and it occurs certainly when the cable is loaded in its limits. So this is the equilibrium equation. Now, certainly this gives us an expression like this, because I to K is equal to if you multiply I to K, it is negative J. This gives us this value minus 4050. Then I have 0.9 J vector here. j to k will give me a positive I vector. From here, I obtain this term. Now here it is 0.9 I vector multiplied by minus f I to k gives us negative j vector. So it is positive value because there is a negative one. So this gives us this term 0.9 f here, 0.6 j vector multiplied by minus fk will give us negative 0.6 f vector, and certainly from mi I have the miy and miz k vector. Now since I have ma x I vector plus ma z k vector plus, just make a correction to the expression. So I is a vector, k is a vector. Sorry, it is maz. Let me write it separately here. So it is ma x I vector plus ma z k vector plus and I and k are vectors. And of course, this part is 0. This is 0. I just change it a little bit. Okay, so this is my equation. So I have max minus 0.6 f plus 0.9 faz minus 4050 plus 0.9 f. Now here it comes. I don't have any k component in the moment equation. Therefore, I can easily say that maz is equal to 0. Now, since maz is equal to 0, I'm left with this equation and this equation. And here I have t plus faz minus f. Now I have two equations, and here I have max, f, and faz. So I have three equations with three unknowns. And the point is this: from this expression, I can easily calculate the value of f. If you do it, you can find the value for the f. It is 4,500. Once you find the f, you can find the faz from this equation. And it will give you, not from this one, from this one. So remember that T is 1,500, F is 4,500, and this has to be equal to 0. From here, FAZ can be easily found as 3,000 newtons. Now, if you substitute it here, so it is 0.6 multiplied by 4,500 plus 0.9 multiplied by 3,000 will give you 0. So this term vanishes. This means that MAX is also 0.